Good day and welcome to the Moscow Telecommunication Seminar. Our today's speaker is Ruslan Yusupov. Ruslan has received a master's degree from the Moscow Institute of Physics and Technology in 2018. Since 2014, he has been working in the Network Protocols Research Laboratory of the Institute for Information Transmission Problems. He has co-authored several conference publications and journal papers. Today, he is going to tell us about different approaches to model restricted access window mechanism in the IEEE 802.11ah networks. Ruslan, the floor is yours.
All right, thank you, Vyacheslav. All right, so let me start. Good day, everyone. Thank you for the introduction. Today, I'm going to give a brief image on the mathematical models that have been used to model the restricted access window mechanism. I don't want to go very deep into the details, but rather try to give a very broad view on the modeling approaches. Since the RO mechanism has been introduced in the IEEE 802.11ah standard, it has attracted the significant attention from the international research community. However, today we are going to talk only about the models that have been developed outside of the IEEE. If you have any questions, please at any time do not hesitate to interrupt me and ask your questions. At first, let me briefly recall some certain peculiarities of the RO mechanism. RO mechanism has been introduced in the IEEE 802.11ah standard. The standard has been developed to satisfy the needs of Internet of Things. It supports up to 8,000 plus simultaneously connected stations in range up to 1 kilometer, thanks to the use of sub-1 gigahertz frequency band. Large number of stations that are simultaneously trying to obtain access to the channel results in a high contention for the channel when legacy random channel access methods are used, such as EDCA. So high contention for the channel leads to increased number of collisions before the frame delivery and correspondingly to increased energy consumption. In the typical IT scenarios that the 802.11ah standard has been developed for, there might be stations, like for example, IoT sensors, that has autonomous power supply and might need to save the energy to enable the long device lifetime. So the 802.11ah standard introduces the RO mechanism that allows to protect such low energy consumption demanding stations from contention with a large number of another device in the network. When the restricted access window mechanism is used, the access point defines a special time interval called restricted access window, or simply RO, and selects a set of stations that are allowed to transmit within the RO. This allows to protect such low energy consumption demanding stations from contention for the channel with the other stations. To reduce the contention for the channel even more, the access point can divide the RO into several RO slots, and selected set of stations can be divided into groups. Each group is allocated with one RO slot and allowed to access the channel only within the allocated slot. Within the RO slot, stations that are allocated to this RO slot use the enchanted distributed channel access method with access category defined by the access point. However, the standard introduces certain details related to the EDCA usage that we need to mention. So first detail is that within the RO slot, stations have to use a separate EDCA state machine. When station enters the RO, the station freezes old EDCA state machine and set up a new one with 0 retry counters and minimal contention window. The new EDCA state machine is used when stations access the channel within the RO slot, within the allocated RO slot. When station exits the RO slot, it removes a new EDCA state machine and returns to the old one that was frozen. So from the point of view of the old EDCA state machine, the restricted access window is like a time interval that doesn't exist, in the meaning that raw operation doesn't affect or in any way changes the state of the EDCA state machine. The new EDCA state machine, however, since it exists only within the raw slot, it can see only the contention conditions within the allocated within the corresponding raw slot. One of the possible reasons for that behavior is that within the raw, the set of stations that are allowed to act as a channel to contend for the channel is different from the set of stations outside of the raw. So it means that the channel conditions outside and inside the raw are different, and we need to stop a new EDCA state machine to make the EDCA to reflect such change in contention conditions. The second detail is so-called cross-slot boundary flag. Cross-slot boundary flag is defined in .11h standard, and it controls, it is set up by the access point. The access point sends information about the cross-slot boundary flag when raw is set up. And cross-slot boundary flag controls behavior on the raw slot and border. So when the cross-slot boundary flag is set to 0, stations allocated to the raw slot are not allowed to start any frame exchange sequence that ends after the end of the allocated raw slot. It means that, or rather, usually in the paper we see such entity as closing period, which is the interval of time at the end of the raw slot where stations cannot start any new transmission attempt, but can end their old transmission attempts. When the cross-slot boundary flag is set to 1, station is allowed to either, if it has 0 block-off counter value within the allocated raw slot, start one transmission attempt which crosses the raw slot end boundary and ends in the next to the allocated raw slot. Or if it doesn't have 0 block-off counter value within the allocated raw slot, it may count down the block-off counter in the next to the allocated raw slot and start one transmission attempt, only one transmission attempt after the end of the allocated raw slot. So that's all regarding the details about the raw mechanism from the .11h standard. Since within the raw slots, stations use the EDCA channel access method, the EDCA method, one of the ideas to model behavior of transmission process within the raw is to use well-known Bianchi model. Now I want to recall some certain properties of the Bianchi model that we are going to refer future in the talk. So originally, in the paper devoted to the DCF method, Bianchi considered a stochastic back-off process at some arbitrarily selected station. The process includes current back-off stage and value of the back-off counter, and it is modeled as a discrete time Markov chain. The unit of time within that chain is the virtual slot, which is usually defined as the interval of time between consecutive changes of the back-off counter. In that Markov chain, part of the states corresponds to the process of listening to the channel and decrementing the back-off counter based on the information gained from the channel listening. Another part is responsible for the modeling of the transmission attempt, which might be successful or collide because of the transmission of other stations. Assuming that the probability of collision doesn't depend on the current back-off stage and considering the steady state of the Markov chain, it is possible to estimate the probability that randomly chosen station transmits at randomly chosen virtual slot, and also estimate the conditional collision probability that the collision happens during the transmission attempt. And thus, we obtain nonlinear system of equations, and by solving it, it is possible to find both tau and p probabilities, and further use them to calculate necessary network KPIs. So the Bianchi model have been introduced many years ago. It has been modified, expanded, and used for the analysis of large number of different scenarios. And several works actually tried to apply the Bianchi model for the analysis of the raw mechanism. In the paper 2, authors apply the Bianchi model and try to find optimal number of row slots that maximizes the transmission, the successful transmission probability within the row slot, based on the number of stations, based on the number of stations that are allowed to access the channel within the row. In the third paper, authors propose an extension of the Bianchi model for the row mechanism that takes into account the probability of frame corruption due to the channel noise. Finally, in the paper 4, authors use the Bianchi model. Authors just applied the Bianchi model directly for the raw mechanism to find the energy consumption of the devices, and then they further use that model to find optimal parameters of the raw mechanism that maximize the energy efficiency of the network. So, apart from the Bianchi model, there has been slightly different approaches to model the raw mechanism, and one of them is we are going to refer as to the JSDCF model. And the original papers have been written in 2013. Authors wrote 2 papers. They introduced the model in the conference paper and significantly extend the JSDCF model in the journal paper. However, there might be a certain misunderstanding because of the terminology. So, actually, in the context of their paper, authors consider the restricted access window mechanism. And the restricted access window, they say that it is a predefined time interval during which authors in which stations use DCF method as a channel access method. And that method, where stations are divided into groups and access channel within groups in a certain predefined time intervals according using DCF method, they define this method as DSDCF or group synchronized DCF method. However, in the context of our presentation, we call the same thing as a raw mechanism. So essentially, JSDCF and raw mechanism are the same entities in the context of our presentation. So the JSDCF model is based on Bianchi model, but authors try to take into account the finite duration of the row slot. So probabilities tau and p in JSDCF model are taken from Bianchi model according to formulas from Bianchi model. However, as the next step, authors of JSDCF model try to find the distribution in the number of successful transmission attempts, or rather the distribution on the number of transmission attempts that can fit into the row slot of finite length. In order to do that, they model the distribution of the number of empty virtual slots between the transmission attempts as a random value with geometric distribution. This allows to model the total number of empty virtual slots that happens between the beginning of the row slot and end of mth transmission attempt as a sum of geometrically distributed values that have a negative, that is a random value with a negative binomial distribution. If we know how much empty virtual slots and transmission attempts have happened, we can find the total duration from the beginning of the row slot until the end of mth transmission attempt. So essentially, that negative binomial distribution allows to find the distribution of time passed from the beginning of the row slot until the end of mth transmission attempt. And this allows to find the distribution of number of transmission attempts that might have happened within the row slot with finite duration. That model allows to take into account also different durations of holding period, obviously, and probability that certain transmission attempt is going to be successful can be found, can be taken again from the Yanchi model. And for the non-cross-slot boundary case, first paper, conference paper, gives pretty much mathematical model that allows to model. So regarding the cross-slot boundary, we need to take into account the fact that there might be transmissions from the previous row slots that occupy certain space at the beginning of considered row slot. So essentially, authors of JSDTF model discretize that occupied time in the units of empty virtual slot lengths. And if we know how much time have been occupied by the transmission from the previous row slot that is crossing the slot boundary, then we can use the approach described before to model, to find the distribution of time that the last transaction started in the allocated row slot and ended which cross the row slot boundary and ends in the next to the allocated row slot. The distribution of time that such transmission occupies in the next row slot. So essentially, if we say that transmission from the previous row slot occupies empty virtual slots, or length of empty virtual slots at the beginning of allocated row slot, then we can, given that value, we can find the distribution of the length of the transmission, the distribution of occupied length in empty virtual slot units that will be occupied by the transmission crossing the considered row slot boundary. In that way, we can consider again Markov chain, find the steady state of that Markov chain, and thus find the distribution of the length available length of the row slot, of the length available to the transactions in the current slot. So that approach allows to model the cross-slot boundary case, and it has been described in the extended journal version of the model. Apart from two original papers where the JSDTF model have been introduced and described, there is some papers that use the JSDTF model for their own purposes. The paper number 7 extends the analysis from the original paper and consider various additional options regarding the behavior of the Bukov counter during the holding period at the end of the row slot in the non-cross slot boundary case. the paper 9 consider proposed to select the row slot length according to the number of stations allocated to the row slot. And finally, the paper 9 uses the JZCF model as a basis for the algorithm that tries to choose the group's allocation and parameters of the row mechanism in order to satisfy the quality of service requirements of stations with heterogeneous applications. Last model we will try to highlight in this talk is so-called message model. Here it is named just under the family of two authors of the corresponding papers. So from the first side, message model looks pretty similar to the branch model. The definitions for probabilities tau and p have been taken from the branch model, but for now, in message model, we do not consider virtual slots. We just consider back-off mini slots. Yeah, these probabilities tau and p are normalized into back-off mini slots. Also, message model tries to take into account holding period at the end of the row slot and reinitialization of the back-off counter at the beginning of the row slot. So the discrete time Markov chain considered in message model also looks pretty similar to the original Markov chain from branch model. However, there is certain differences. At first, since message model considers not saturated traffic but Poisson traffic flow, there is a special state that tracks the income of packets into the empty station queue. After the packet income, the chain goes into the synchronization state, which tracks the process of waiting within the beacon wall until the next allocated row slot. After that, there is part similar to branch model where stations count down the back-off counters, and when the back-off counter equals to 0, they try to make a transmission attempt. However, since in message model the time unit is not the virtual slot but back-off mini slot, there is a certain loopback probability that station listens for another transmission attempt or another collision and doesn't decrement the back-off counter. Finally, when station has 0 back-off counter value, it might either transmit packets from the queue, and if there is packets in the queue, it goes into the synchronization state, waits for the next row slot. If the station queue is empty, it goes into the idle state and waits until the new packet arrival. And if station counts down the back-off value, the back-off counter, and but there is not enough time until the end of the row slot, then it goes into the delay state where it waits until the end of the holding period at the end of the row slot, and then goes into the synchronization state to wait until the next row slot. Unfortunately, message model doesn't consider crosstalk boundary case. However, in the journal version of the paper, the model has been extended to consider the ADCA method with several access categories. So that actually ends my talk. Today we did not discuss models developed within the ITP. These models are planned to be discussed next time. Thank you for attention. If you have any questions, I'll be glad to answer them.
Ruslan, thank you for your talk. My question is, could you repeat why can't we use Bianchi approach to model cross-law boundary and all other peculiarities of law? Why do we need Mishich and JSDCF approaches?
Well, actually, I didn't mention that. Thank you for your question. So, the original bench model have been designed for saturated traffic, and it as I mentioned before, there is certain peculiarities regarding the behavior of the EDCA state machine at the Ruslan boundaries. At the beginning of the Ruslan, we have to freeze all EDCA state machine and set up a new one. New EDCA state machine is initialized with minimal contention window and with zero short and long try counters, pure try counters. So essentially, in the Bianchi model, we are going to start from somewhere on the first row at the beginning of at each beginning of the Ruslan. Then, as Ruslan ends, at a certain time moment, we are gonna have to stop our transmission attempts because we cannot make a transmission attempt that doesn't process the Ruslan boundary, which essentially means that all stations that would go into the stochastic process, they would end somewhere in this Markov chain. And at the beginning of the next allocated cross-slot, stations should again reset the EDCA state machines because the state of the EDCA state machine that is used outside, that is used inside of the Ruslan, it was not safe. So at the beginning of each Ruslan, we are going to start with zero Bukov stage, on zero Bukov stage, no matter how we ended at the end of the previous Ruslan. So essentially, it means that the stochastic process that is modeled by Bianchi model, by the Markov chain from the Bianchi model, it is going to be reset. It is going to be reset every time the Ruslan ends and starts a new one. Bianchi model, however, considers the steady state. It doesn't consider any resets of the stochastic process. And technically, it is possible to use Bianchi model if we consider Ruslan with infinite length. Because in that case, stochastic process that have started in such infinite length Ruslan, it is gonna converge to the steady state, and the Bianchi model would be pretty much accurate. However, if we want to consider Ruslans with finite length, we need to take into account that at some points the stochastic process is going to be reset. The GSDCF model doesn't consider reset of the stochastic process. However, at least it takes into account the fact that at certain time moment we cannot make further transmissions, and there might be only a finite number of transactions that can be made within the Ruslan. Regarding the message model, there is certain transitions that take both the holding period at the end of the row slot and resynchronization and reinitialization of the stochastic process at the beginning of the next row slot. Such as, for example, when we are counting down the Bokov counter and ready, and at a certain point the Bokov counter equals to 0 and we are ready to make another transmission attempt, with certain probability, that transmission attempt cannot be made because we already reached the end of the row slot. And in that case, we need to go, we need to wait until the next row slot. In message model, that is modeled as a delay state where stations should wait until the holding period ends. During the holding period, station, if it counted down the Bokov counter to 0 within the holding period, it cannot start the transmission. However, there might be still certain other station transmissions that ends within the holding period. They just should not cross the row slot boundary in the non-cross the row slot boundary case. After the holding period, stations go into the synchronization state, and in the synchronization state, they wait for the next row slot. And at the beginning of the next row slot, from the synchronization state, again, we go into the zero Bokov stage. So basically, if in short, GSDCF model is capable of taking into account finite length of the row slot, since they consider distribution on the number of transmission attempts within the row slot. And message model is capable of taking into account both the holding period at the end of the row slot and reset of the stochastic process or reset of the ETA state machine at the beginning of row slot. Should I provide other details?
No, just please summarize. So as I understand, like the Bianchi model is the least accurate model to model the row mechanism, and the message model is the most accurate model. Am I correct?
In general, yes. There might be certain details related to different scenarios, but in general, I would say yes, that's correct. And GSDCF model is somewhere in the middle.
Okay, but do the authors of message model compare accuracy of their model comparing to the GSDCF or Bianchi model or something like this? Because I understand that GSDCF doesn't take into account some details of row mechanisms, but maybe these details do not impact the overall performance indicators, for example, throughput or other things which are calculated by the message model. So do they compare with other models?
Yeah, that's a good point, and no, they doesn't compare. Maybe the accuracy of the GSDCF model is pretty much enough for majority of scenarios. However, there is no such comparison in the literature.
Thank you. So maybe one more question from me, from my side. When you tell us about GSDCF model, you first described the model without cross-slope boundary, as I remember, and then give us generalization of the model to support cross-loop boundary. My question is, this generalization seems to be quite complex. So my question is whether the cross-loop boundary significantly impacts the performance of raw slot, or we can do not take it just into account the possibility that cross-slot boundary is enabled.
So it's also a very good question. I don't have any numerical results for now. However, the idea of enabling the cross-loop boundary is that, again, there is a certain holding period in the non-cross-loop boundary case where stations cannot start transmissions. And that holding period is actually, in some sense, waste of the channel time, in the meaning that literally we have at the end of the raw slot a certain fraction of time where we cannot start the transmission, even if we have packet in the queue. However, this time at the end of the raw slot, it is going to be free if nobody starts the transmission right before the holding period and occupies a major part of it. So enabling the cross-loop boundary allows us to kind of use that holding period and do not waste it. However, it brings us only one transmission attempt, only one additional transmission attempt, and we don't even know because this transmission attempt might also collide. There might happen something. So the transmission attempt is not guaranteed to be successful, obviously. So I can assume that in case of long enough raw slots, enabling or disabling the cross-loop boundary would not affect the network performance in any significant way. There is certain results, not in the papers, not in the JSDCF paper, in some other papers, that shows that enabling the cross-loop boundary allows to slightly improve, less than 10% gain, slightly improve the throughput, the network throughput, by the cost of increased energy consumption, because it is more likely that certain transmissions will collide if we allow for more transmissions. However, for long slots, I assume the difference should not be significant, while for short slots, it is actually hard to tell.
Okay, thank you. So just for short raw slots, we have to take into account cross-loop boundary in our models to have accurate results. Yeah.
Yes, and if a raw slot is very short, like if the length of the raw slot is comparable with the length of the transaction, then enabling or disabling cross-loop boundary might have pretty much significant impact. Although, again, I don't have any numerical data to support that assumption.
So I guess that's all questions. Thank you, Ruslan, for your presentation, and thank you all the participants for participation in the seminar. The next seminar will be held next week, and it will be about non-orthogonal multiple access in Wi-Fi networks. So see you next week. Thank you all.